Hi guys, let's learn another new concept, potential energy of system of charges. So in this concept we will deal with several sub concepts. So like that, in the first case, potential energy of a single charge in the absence of electric field. Parallelly, we will deal with the same potential energy of a single charge in the presence of electric field. Okay. After that, we will take the two charges in the absence of the electric field and in the presence of the electric field. So like that, we will go first. Let me take potential energy of a single charge in the absence of electric field. Now, you would remember two formulas. So the very first one I can write that. So according to potential difference formula, potential difference is equal to work done upon test charge. So here I can write potential difference VB minus VA equal to work done W upon test charge. You can take in terms of the Q. So this is the first formula. Another formula, whatever the work we do, that work will store in the form of the potential energy. So that concept we already knew that, so that I can write the work done is stored in the form of potential energy. So for this, let's take a small example. Suppose you are having a stone on the ground. So this is a stone of mass capital M. So it is located on the ground. Now here potential energy you can take. So the potential energy is equal to 0. Suppose I lifted to this stone at a height. So this at a height as h. Now here the potential energy, you know that it's having the potential energy in terms of mgh. So how did it get the mgh? Because I lifted from here to there. So I did work. So whatever the work I did, so the work done is stored in the form of potential energy. So this happens when the force is conservative force. So anyway, this gravity and electrostatic forces are conservative in nature. So whatever the work we do, so that will be stored in the form of potential energy. So this is the basic knowledge I need to take you further. So first, let us discuss the first case at here. Potential energy of a single charge in the absence of electric field. So let me draw a line so that it should not. Oh my god. Okay. Now potential energy of a single charge in the absence of electric field. So how we define the electric potential? So the electric potential we define as the work done to bring a charge from infinity to a location, a point P in the electric field. So here no electric field, so there is no opposing force. If there is no opposing force, there is no work done. So the work done to bring a single charge in the absence of electric field. So that work done equal to 0. There is no need to do any work because here there is no charge. Just imagine that you are carrying a positive charge from infinity to where there is no electric field. If there is a positive electric field, so these two charges will be repel each other. So we need to do work against the electric field. But at here, there is no electric field. It is in the absence of electric field. If it is in the absence of electric field, there is no need to do any work. So even though we are bringing a charge, but there is no opposing force. So whatever work we do, so that work will becomes 0. So that's about potential energy of a single charge in the absence of electric field. But take a case, potential energy of a single charge in the presence of electric field. What makes the difference at here? For that, let me take an electric field. I am taking an arbitrary electric field. Suppose this is electric field. So let me take two more lines. So this is the electric field randomly, electric field direction. Okay. Now here the electric field is present. Now if I chose a coordinate system, so in this one, in this electric field, if I chose a coordinate system, so this is the coordinate system. So in this coordinate system, I will take a location. So suppose from this origin, I will take at a point. So because we need to specify the point at a location R1, at a point P if we can take. So this P is at a distance of R1 from the origin. So this you are free to choose coordinate axis. Now what we define? We need to define what is the potential energy at this location. So that is our task. So for that what we have to do? We have to go all the way from infinity and we need to bring a test charge. Let here Q is my test charge. So I am bringing all the way from infinity to a location point P. And we already knew that since this point P is within the electric field, so we already defined potential at here. So we know that one at point P potential is already exist. If the potential at point P equal to V of R1, so here R1 why I am writing, so that tells about where the point P is. Okay, nothing like that. Otherwise, we will get confused what is the exact location of the potential. Now that is the potential due to because of the electric field at point P. So that we used to represent V of R1. Now if we can write similarly the potential at infinity. So the potential at infinity. So we used to take that potential as 0. Why? Because potential is inversely proportional to R. So when R tends to infinity, so potential goes to 0. Okay. Now here we will define the potential difference. So potential difference, what we can write? Potential difference Vp minus V infinity, that is the potential difference, which equal to work done per test charge. Now, what is the potential at point P? So that I have taken as potential V of R1, and what is the potential at infinity? That equal to 0, which equal to work done per test charge. So in simple words, you can write V of R1 equal to work done per charge. Therefore, work done equal to potential at location R1 times test charge. So this is the work we need to do to bring a charge from infinity to location P within the electric field. Now, this work done will store in the form of potential energy. So if you mention that the work done is stored as the potential energy of the charge, the work done is stored as the potential energy of the charge. So we will replace W with U. So U we used to represent for the potential energy. Now if you can replace that in this above equation at here, now it will be changes as U equal to potential at location R1 times charge. So this is the potential energy of a single charge at a location within the electric field. So the U stands for the potential energy, Q stands for a single charge, and V of R is the electric potential at a location. Okay, now this is the expression for electric potential energy. So electric potential energy. Electric potential energy for a single charge in an electric field. For a single charge in an electric field. Now we will see potential energy of a 2-point charges. It is a 2-point charges in the absence of electric field. So parallel here, potential energy of a 2-point charges in the presence of electric field. So first let us deal with the in the absence of electric field. Now consider I am having 2-point charges. If I can mention that as Q1 and Q2. Now I need to find the potential energy of these 2-point charges in the absence of electric field. Now for that, first I will bring this Q1 charge. So the work done to bring charge Q1 at a location point P. So work done to bring Q1 at point P equal to, so if you can mention that as W suffix 1, which equal to it's 0, because there is no external force which is acting over me, so there is no opposing force, so my total work done will become 0. So I already brought a charge Q1 at a location P. So this is at a point P. Now because of this charge, now electric field is exist. Okay, now because of this charge, now at here the electric field is exist. Now if I bring charge another Q2 at here, by the time the work done is not equal to 0. Okay, now that is my second task. Now if I am going to bring a charge q2 from infinity to at a point at here, if you can take at a point q, so one more q already is there, if you can take at a point k, so work done to bring q2 at point k. So now I need to find what is this perpendicular, what is this distance from here to there. Now if I consider that distance as r12, now this is the location of the charge q2. Now we will write the potential difference formula. So what is the potential difference formula? So potential difference, I can take another color so you can see clearly. So potential difference equal to work done upon test charge. Now here the potential difference, we can mention that potential difference, that is at a distance r12 at location k. Otherwise, if you can get confused, write it as simple as you can, so that you can write as potential at point k minus potential at infinity, then only you can get the difference. So that is the work done. Here the my test charge. Now I am bringing test charge q2. Now if you can further write potential at k due to the charge q1, because at k already due to q1 potential is exist. Now we can write the mention the potential formula, that is k q1 upon r12, that is the original potential formula. How we can write the potential formula? Potential V is equal to k capital Q by R. So here capital Q is a source charge and R is a distance. Minus potential at infinity, you can take as 0, which is equal to work done upon charge q2. Now you can write the work equal to k q1 q2 upon r12. So this is the work done to bring second charge. Okay, so to bring the charge q2. Now if I mention that as to mention at here, what we can write the total work done? So the total work done equal to W1 plus W. Since we need to write for the two system of charges, therefore total work done is equal to W1 plus W. So W1 goes to 0 and the W value equal to K Q1 Q2 upon R12. So this work done will be stored in the form of potential energy. So I can mention that as potential energy U equal to, therefore potential energy U equal to K Q1 Q2 upon R12. So this is the expression for potential energy due to system of two charges in the absence of electric field. Now we will see what is the potential energy for a system of 2-point charges in the presence of electric field. So let me take an arbitrary electric field. Suppose this is an electric field direction, random. Some electric field is existing. Now if I draw a coordinate axis, so within the electric field, So this is my coordinate axis. Now I'm having 2 point charges. So let me take that as at infinity. So let me Q1 and Q2. So they are at infinity. And I need to calculate what is the potential energy due to these 2 charges in the electric field. Suppose if I bring Q1 at a location R1 within the electric field, suppose this is the location. If I can take a location at here which is at a distance of R1. Now I need to bring a charge Q1 from infinity. We'll bring a charge Q1 from infinity all the way to at this location. Okay. Now we can write that at location at A, we can mention that. So what the work we can write? The work done, or we can mention that as potential difference is equal to work done upon test charge. Now potential difference, potential at point A minus potential at infinity, which equal to work done upon test charge. Here I am bringing a test charge of Q1. Now at point A, potential is exist because of this electric field. So if I mention that potential at point A equal to, so potential, how we can write the potential formula? So from the earlier definition we can take that as a at here. So the potential at a location or work done to bring a charge, so that we can mention as, so VA we can write that as potential at R, potential at a location R minus potential at infinity goes to 0, that equal to work done. So this work done you just mention as W1 upon Q1. So therefore W1 equal to potential at a location at a distance R1 times Q1. Okay, so this is the potential energy. This work done will be stored in the form of the potential energy, which also equals to, which I can write U1, which equal to V times R1 times Q1, because work done is equal to potential energy stored. Now to bring a charge another Q2. Now if you can take, I need to bring a charge Q2 from infinity. So this is at a location of infinity. Now I all the way to bring a location. So let me take this as a location, a point B. Now this location is at a distance of R2 from the origin. Now if you write the same potential formula for this case, now we can write the same formula, potential at B minus potential at infinity, which equal to, so in this case I can call that as a work done W2, and this time I am bringing the charge Q2. Now we will write the potential at B as potential V times R2 minus infinity, which equal to W2 upon Q2. Therefore work done to, which equal to V times R2 times Q2. So this is the work done to bring another charge from infinity to at a location R2 in the electric field. Now this work done will be stored in the form of the potential energy. So we can write that as U suffix 2 equal to V times R2 times Q2. So here U2 is the potential energy stored in the charge Q2 at that location. So here you can write work done is equal to potential energy. Now if you can write the total potential energy as sum of these two potential energy. And not only that, so in this case if we can see, so this is the charge Q1 and this is the charge Q2, and now they both are at a distance of R12. If they both are at a distance of R12, what is present between? Again, between them, electrostatic repulsive force is present between them. Now, since they both are the positive charges, one each other, they will repel each other. Okay? But there is certain force to keep them together. Now this is the third force which is existing in this case. Now I can write that as work done on Q2 against the force exerted by Q1. So this we can write as work done on Q2 against by the force Q1, which equal to K Coulomb constant Q1 Q2 upon R12. So this is the electric field formula. Now this is also the work done, so which is also stores in the form of the potential energy. So this we can mention that as U3, which equal to K Q1 Q2 upon R12. Now what is the total potential energy of the system? Now to write the total potential energy of system, we need to combine the work done to bring charge Q1 and the work done bring charge Q2 plus the repulsive force which is present. To overcome the repulsive force, some work has to do between the two charges. So that we should add. So here the total potential energy as total potential energy of two point charges in an electric field. In an electric field is, you can combine U1 plus U2 plus U3 which equal to U. That is the total potential energy. So if you can combine the three potential energies, if you can write that as, so if you can take that U1 equal to V R1 of Q1 and U2, that is the potential at R2 due to charge Q2, plus K Q1 Q2 upon R12. So this is the total potential energy. So this is the total potential energy of the 2 point charges in an electric field. So here you need to concentrate how did the third term is appeared. So the third term is appeared is due to because they both are the same charges. There is a Coulomb repulsive force is there, but to keep that two charges together, so this is charge at Q1 and this is charge Q at Q2. Since they both are positive charges Q1 Q2, they are repelling each other. To keep together, some work has to be done. So here that work is done by the external electric field. So that component here we need to add. So here the three terms will be exist. So this is the expression for the total electric field. Sorry, total potential energy of 2 point charges in an electric field.